All right, well, welcome everyone. My name is Sharon White and I'm the marketing manager for BLT. Today's webinar is Debug Techniques for Vivado Block Designs. Before we get started, I just want to take a few minutes to introduce BLT and our speaker and to go over some housekeeping. So to get started, if you have questions, please put them in the chat panel and we will get to them at the Q&A at the end. Today's webinar is being recorded. I will send that recording out once it's ready, which will take a couple of days. There are no books or slides with today's talk. So now let me introduce to you BLT. BLT has been in the engineering design services business for almost 35 years. We were founded in 1989, so almost 35. Our headquarters are in Maryland, and we have a design office in Melbourne, Florida as well. We design chips, boards, software, and complete systems for commercial, aerospace and defense, and intelligence clients. And some of our notable designs include the prototypes for HDTV and satellite radio, and our work on the Mars rover. Our designs are in space, undersea, and everywhere in between. And we've been teaching AMD Xilinx training for over 25 years. We're an AMD Premier Partner, AMD coaching provider, and authorized training provider. Our training is by engineers and for engineers, and we bring our decades of real-world design experience to the classroom. If you're interested in other training and events from BLT, be sure to follow us on LinkedIn, Facebook, Instagram, and X or Twitter. I post all of the latest updates on our social pages, so if you want to be the first in the know about events like this one, be sure to follow us on social. Today's webinar is being led by Eric Davidson. Eric is a project engineer at BLT with a focus on AMD Xilinx devices. His professional work includes PCIe, commercial network switches, multi-purpose RF SOC-based mezzanine cards, and radar systems. Even though Eric works here at BLT, he's actually not a huge fan of BLT sandwiches, neither am I. He's also a CPR first aid instructor for the Red Cross and has been a volunteer EMT. So welcome, Eric.
Thank you, Sharon. Appreciate the introduction, and good afternoon, morning, depending on where you are in the world, to everyone. And as Sharon said, we're going to be going through today and talking about how to debug within Vivado's Block Designer within the IPI, or the IP Integrator, otherwise as the formal name. So we're going to go through a presentation here. This presentation is going to take about 10 to 15 minutes. We'll go through and talk about the different features within IPI for debugging. Primarily going to be focusing on the ILAs and the system ILAs, the two debug cores that are most frequently used, but I'll mention some of the other cores as well that can come in handy for sure. After that, we'll go through and I'll lay out what we're going to go through in our live demo. I'll go through and perform that demo. And after that, we'll go ahead and leave it open for a question and answer session. Overall, I expect the webinar and everything here today to take about an hour, but depending on how many questions we get within the Q&A, we may go a little longer or a little bit shorter. So with that, we'll go ahead and get into the content for today. Starting off with a review of Vivado's IP Integrator. So if you've used Vivado before, you've probably used the IP Integrator. If you haven't, or just haven't run into a case where you've used the integrators, this is just going to provide a little bit of a background on what it is. So within IP Integrator, in working on projects with them, you've probably heard people mention block designs. Block designs are which you're creating with IP Integrator. This is effectively a way where you can create or visually design your project, right? So what does that mean? VHDL, or in VHDL, or just any HDL, you're instantiating modules and components, connecting up to logic, and you're doing all that using text, right? That is very nice in many regards, but in other regards, depending on how people like to interface with things, some people are more visual learners and they like to see things more visually. So Vivado's Block Designer can come in handy there, as you can instantiate components visually, see the ports, and actually manually make all of the visual connections and so on. It has other features such as supporting design hierarchies and nesting block design, so you can make your design nice and clean and visually appealing to look through. Within that, given that it is a space to design HDL, it does also support debug, right? As you might expect. So it supports the common debug cores. So like your ILAs, your system ILAs, like I said, the things we're going to be mostly focusing on today, but it also supports things such as the VIO or the virtual input output. That's where from the hardware manager, you can manually control signals within your design. So a common use case for this is to see if like an MMCM has locked, right? Send that to a VIO, and you can just see right from the hardware manager, oh, is the lock high or is the lock low, right? So another case for that can be like a reset. So you can just, in your VIO, just say, hey, I want to use a reset, or I want to control a reset right from the hardware manager. You can do that, and you can control the reset within the FPGA straight from the hardware manager, which is amazing. So a couple other things you can do, of course, are to insert debug cores directly into a netlist. So if you're familiar with Vivado's debug core and debugging techniques, you'll know the netlist insertion flow and the HDL instantiation flow are two different ways that you can get debug cores into your design. So this is mentioning that the Vivado IP Integrator allows you to use the or referred to as the netlist insertion flow to mark nets as debug and then later input debug cores once you've gone through the synthesis stage. All right, and then there at the bottom, those final couple of boxes are talking more specifically about the ILAs. I won't go too much in depth with those right now because we're going to get more in depth with those just in a few slides here. But mostly saying that, of course, Vivado's design suite IPI does support those ILAs, and that allows you to monitor signals. So, right, if you have some kind of an interface and you want to see what data is going over that interface, what you could do, set up an ILA on that interface, connect up the probes, and then go into the hardware manager once you have a bit stream and you're loaded onto your FPGA, set up a trigger and tell it to capture the data that's going across that interface when that trigger condition is met, and then analyze the data for whatever purposes, whether that's debug or just validating to make sure things are working. Okay, so there's a couple different approaches that you can take to debug within IPI. I've hinted at most of these already. The first approach is just to go through and directly mark the nets of interest as debug nets. So they show you a little example on how they're doing it there. You just simply find the net of interest into your design, simply right click on it and say mark it as debug. Simple as that. Another way is to add the debug cores just like you would anything else into the Vivado block design. You go through your your IP catalog, select whatever core you want. So in this case, they selected a VIO or even an ILA. Place that core or double click on that core to create an instance of it, customize it as you need it to be customized, then go ahead and add it and connect it up into your block design. Final way is through using HDL attributes. So this is more relevant if you are instantiating modules in your block design that are custom RTL modules. So you can instantiate those custom RTL modules, continue to use the mark debug attribute, so the netlist insertion flow style, adding debug cores to your project. You can continue to add those, add that module to your block design, and then that attribute will remain through the process of building through synthesis. So then you can go ahead and add in the ILA if you so choose at that stage. All right, so here's an example of example of a couple of steps here of what you might go through if you wanted to add a ILA into your block design. So first thing you're going to do is go to your block design and click on the Add IP button. If you don't have any blocks in your block design, you'll see in the center of the screen, there's just an Add button you can click. If you already have blocks, then at the top banner, there will be a plus button where you can just add the IP through there. From there, go ahead and search for whatever IP you're trying to add. In this case, we're adding an ILA. Then double click that, customize it, and then connect it up, connect all of your probes up. All right, so getting more into the system ILA now. So many are likely familiar with the ILA the integrated logic analyzer, and what it offers. So providing you the ability to capture data within your FPGA on specific trigger conditions. The system ILA is kind of the next, uh, uh, it is an ILA with additional features effectively, right? So the system ILA is an ILA which is interface aware, right? So, and a lot of our designs, especially a lot of designs that are involving like an MP sock, something with a processor, you're going to have at least a decent number of AXI interfaces. So the system ILA can be very helpful in those circumstances in that it understands what the AXI protocol is, and as such can provide you with more detailed information when you're debugging within Vivado's Hardware Manager. Okay, so just kind of taking a quick step back to adding the ILA in your actual block design. Um, Once you have it created and instantiated in your canvas, the next thing to do would be to actually add that block design to the build flow. If you've used Vivado Block Designer before, you probably are already aware, but in order to build a project with a block design in it, that block design has to be instantiated within an HDL file. The block design itself cannot be the top level of the project. So you need to instantiate it somewhere in your design. Now, if you're at the stage where you're debugging, you probably already have instantiated the block design in your project. But in the case that you haven't, we'll next go through the steps of what that would look like. So first step here would be to simply go to your sources pane and find your block design that you'd like to instantiate. An option is to allow Vivado to create an HDL wrapper for you. So this does exactly what the name suggests in that it creates in VHDL, creates a component for you that you can go ahead and copy and put into your code and then instantiate correctly. All right, you also want to go through the validation stages within the designer. So you can ask it to validate your block design to make sure that everything is connected, right? Like it sees that clocks are connected to the modules that are expecting clocks. It sees that resets and the correct polarity of resets are connected to the modules that are expecting different resets, those kinds of things. It goes through and just does a quick, nice validation of the block design to make sure you have everything connected uh, as required. From there, once you have your wrapper, you know that your block design is valid, go ahead and instantiate the block design within whatever HDL file is relevant. In this case, they're instantiating it in their own, in a custom HDL module, which is the top of their design. From there, just go ahead and generate your bit stream, building out the project as you normally would. All right. So talking more about the system ILA here. So getting into this a little bit more, the benefit of the system ILA is, as I kind of went through a little bit before, is that it will not only capture the interface signals, but it will also validate your AXI transactions for you. So if you're in your design, if you're manually creating AXI transactions with a 6-state machine or something similar, it'll go through and analyze the signals on those transactions and give you information about them. So we'll see a view of what that looks like in the hardware manager here in just a couple of slides, but it can be very nice. The AXI specification, the AXI protocol is not a terribly complex one, but there are still a decent number of signals involved. So it can be really nice to just have the more simple view of, okay, this is when a read transaction is happening, this is when a write transaction is happening. I can just see that. I don't need to go and decode all of the different control signals to figure that out. So the waveform window, which we're about to see here in a moment, is going to show when we're working with a system ILA, a couple of different things. It's going to, of course, show our interface slots. So it's going to show each of the interfaces that we've connected to the system ILA. It's going to show the events, like I mentioned previous, the read transactions, write transactions, those kinds of things, and then the signal groups. So the sets of, these are the signals that are responsible for performing reads. These are the set of signals for performing writes, address, data, or address, response, those different kinds of channels. All right, so here's an example of what the ILA or system ILA would show you within Vivado's hardware manager after they've gone ahead and captured some data. So we have our various slots here. So for example, our slot number 1 here is performing some read and some write transactions, and we see those show up in a nice summary view here, such that we can even hover over the different transactions and see the specific details of what exactly happened at that time, which is really nice. And then of course below that, if you want more fine-grained information on what's happening in the control signals, that information is also there to decode as well. Okay. And this is just showing here that we have multiple slots available to us that are shown. So we've seen slot 0 up here, though it's just the tail end of slot 0. We have slot 1, and then we'll have the remaining slots available down there. If you've used Vivado's simulation tool, you'll be very familiar with what this waveform viewer has to offer. It operates very, very similar way, so it'll be very familiar to you here within Vivado's hardware manager. Okay, so that was a summary of, or that was just a introduction into the Vivado IP Integrator, what it can do, some of the debug capabilities of it, how you can add debug to the IP Integrator, how you can add debug cores more specifically, how you then go and build that design that you've then added debug cores out to Bitstream, and then more specifically, how to then perform debugging with the system ILA. Now we'll next go through a live demo showing a design, a relatively simple design that if you've taken AMD courses before, you've likely seen. And we'll see how to use the ILA and what that looks like within Vivado Hardware Manager. So our objectives here in our live demo, as you might expect, are to use a debug core within Vivado's IPI, show you how to create it, how to instantiate it, how to connect it, how to go through and build out the design, how to then program it on the FPGA, and how to actually use it within Vivado's hardware manager. Our general process here is going to be analyzing the UART LED example project. Again, if you guys have taken AMD courses before, or you've worked around with the different example designs that are available within Vivado Design Suite, you're likely familiar with the UART LED project, but I'll still give a summary of what's going on in that project as well. We'll then go ahead and identify just a suitable location where maybe we'd want to insert an ILA and probe some data signals. Then we'll go ahead and insert that ILA, create a wrapper for the block design so we can build it, so we can build the project that is, and then go ahead and program that. Now we're going to be using the ZCU 104 evaluation board for this. From there, once we have everything programmed onto the board, we'll go ahead and Vivado's hardware manager will populate all of the information that we need that's related to our ILAs or our ILA that we're going to be adding. And we'll go ahead and configure the trigger and capture settings for it, run a trigger, and collect some data, and then take a look at that data. All right, so an overview of the project we're going to be working on. So this, again, is the UART LED project. And what it does is a fairly simple project. It is, as the name implies, mostly a UART interface that just accepts data from some system. In this case, that'll be our PC here. We're going to send over data over our serial pin. That's going to then get debounced and added or transferred over into our clock domain that we're using. From there, that'll get sent into this UART control module. This UART control module will, of course, receive pulses from the baud rate generator, indicating that it should capture the data that's presented on the receive input. Once it has the full 8 bits of data, it's going to present that data to downstream and indicate that that data is valid for consumption. The downstream in this case is an LED control module. On the ZCU 104, where we have 4 LEDs that we're going to be using, 4 of the LEDs on the board we're going to be using for this project. And this LED control module just determines which of the data, right? So we have 8 bits of data that are sent in. Which of these data bits are going to be forwarded to the LEDs, drive those LEDs? Now, for it to make that decision, we have also a button input that comes in, goes through its associated debouncing and putting it into the system's clock domain. And this signal just determines or just tells the LED module which of the higher or lower nibbles of the data should be passed forward to the LED pins. All right. So with that, I'll go ahead and bring up our project. All right, so this is the UART LED project here. I've already gone ahead and opened it up, and then opened up the block design that came with it. So as we mentioned before, this is a UART project, and a pretty good example of how you might use an ILA is just to validate that data is coming across and going through your design, propagating through your design appropriately. We don't necessarily know that there's a bug yet, but we just want to see what's happening within the FPGA. So a good point for this would be simply just to monitor the data lines, right? So we'll take a look and monitor what the receive input looks like. We'll take a look and see what the data output looks like. So what is our actual valid data looking like? And also capture our data ready signal so we know when this data is actually supposed to be valid, and we can look at it from there. So I'd say it makes the most sense to take a look and probe the data lines, data ready, and then the received data as well. So to do that, we'll go ahead and add an ILA to the design. A couple different ways you can do this. As I mentioned before, there's a plus button you can add up here, so you can add the IP through that. That's one way. You can also right click and just add IP, whatever is easiest for you. So add the ILA, double click on that. Right, and move our ILA to the side here so it's easier to connect up. Go ahead and open that for us. And we'll configure it to just be the native interface. So we just want probe ports. We don't want to ask for an AXI interface. The standard ILA has the ability to capture an AXI interface, but remember that the system ILA is the one that is interface aware, that can accept multiple interfaces at the same time and provide you that nice information that we saw in the hardware or in the waveform in the hardware manager, showing each of the read and the write transactions. So we identified that we want to capture 3 different signals. So we'll say we want 3 probes. In terms of the sample depth, so how many samples of each probe we want to capture per trigger, or how many samples total do we want the ILA to be able to hold at any one time. We'll set that to say 32,768 should be more than sufficient. Okay. And everything else we can go ahead and leave as their defaults. Moving on to the actual probe ports, we can configure that. So we need one of these to be 8 wide, because we have that data bus that's 8 wide that we need to capture. And the remainder of those settings we can leave at their defaults as well. Give this just a moment to go ahead and configure. All right, and we can go ahead and start connecting up. So we'll connect our clock to our clock, our first probe to our data, our next probe to the data ready, and then the final probe will be to our serial input, our debounced serial input, should I say. All right, so now we have our ILA all added into the design. We have a clock connected to it. We have all of our probes connected to it. At this point, we can go ahead and validate our design. So if we just go to Tools, Validate Design, and make sure everything is connected as it expects. So far, so good. Everything looks to be in working order. So next thing we'll do is we'll go ahead and save our project so we don't forget, and add or create rather a HDL wrapper to wrap around this block design that we've created. So if we just select the block design, then right click, we can hit create HDL wrapper. In this instance, we'll let Vivado manage the wrapper and auto update. So if we were to change ports that exist within this block design, Vivado will take care of updating the wrapper for us. We don't have to go and manually do it. So let Vivado take care of that for us. It's pretty convenient. We'll just give that a few moments to go ahead and generate. And here in just a moment, you'll see the sources tab update with that new wrapper. All right, so we have our wrapper here. And if we open up the hierarchy, we see that we have our wrapper and underneath our block design, just as we expected. And we can also open up the wrapper, take a look at it, and we see, oh, hey, look at that. It goes ahead and creates our design as we expect. It's great. Now we can go ahead and generate through Bitstream. Save a little bit of time. I've already gone ahead and created a project and generated the Bitstream results of this. So I'm going to go ahead now and open up Vivado's hardware manager. And to do that, I'm going to close the project and open the hardware manager. If you've gone through the generate bitstream step, you can just open the hardware manager right from within the project. But since I did it in a different project, I'm going to be just closing the project in total. So open up the hardware manager here. All right, then I'll turn on our board. Give that just a moment. All right. And from there, we'll go ahead and open our target, connect to our board. Let's give this just a few moments. All right. So now we'll right click and program. And we will program our file here. Notice that it auto-populated with the LTX file. The LTX file is going to contain all of the information for the debug cores in your project. So that's going to tell the hardware manager here what debug cores exist, what the probes are, and it's going to give it all the information that it needs to, for us to interact with the debug cores in the actual FPGA. So we're just going to give that a moment to program up, and then for the hardware manager to go ahead and set up our interface for our debug cores, which in this case is just an ILA. All right, great. So now we've got our ILA up here. Ignore the VIO. This is from an old project. That dashboard isn't relevant to this project. So we have our ILA here. We have our data signal, our data ready, and that debounced version of the serial data that we connected. So what we're going to want to do here is we can first go ahead and configure our capture settings. So if we go to the settings pane here, we can specify a number of different information on how we want the ILA to capture data for us. So first thing, we want just one data window. You can modify this if you choose. So if we say 2 data windows, then it will wait for 2 instances of the trigger condition to occur, and it'll show you those 2 sets of data associated. Now, of course, as you increase the number of data windows, so say if we had 2 data windows here, you would have 16,000 of the 32,000 um, uh, probe or data points available for each of the 2 windows. So it just splits it right in half. As you saw there, when I clicked out of the box, it updated. So we'll just go back to a single probe or a single window, and we'll specify the maximum data depth. This is the setting that we set in the ILA earlier. We told it that we wanted 32,000 samples to be collected. So we're just setting that to the max. And our trigger position in window, for this, we can go ahead and specify 8,192. This will give us some samples that occur before the trigger. So 8,192 samples before the trigger. The trigger will then occur, and then the remainder of samples will be the data captured after the trigger occurs. So now that we've got our capture window or our capture settings configured, we can go ahead and set up our trigger settings. So to that, we want to trigger when we see that the data is ready. Seems like a reasonable trigger. So we'll add that, and then we'll say the value. We want the trigger to occur when we see a rising edge on Rx data ready. All right, so now we have our waveform window configured, our ILA is configured, the capture settings and the actual trigger all ready to go. I'll go ahead and pull up our serial terminal now. And for this, we're going to be using TerraTerm. And just a moment while I get this set up. So we have our serial terminal here. And just to show you what the FPGA looks like, what the behavior of the LEDs are when we are using this device, I can show you that here. So if you can see, you see the 4 LEDs here. They're kind of around the buttons there, and you'll see as I enter different data in, you'll see those LEDs. Or as I send different characters, you'll see those different LEDs shine bright, light up in response to that. So now what we're going to do is we're going to go ahead and start our ILA here. So we're going to say go ahead and run the trigger. So now it's going to be waiting for a trigger. You'll see it immediately captures all of the data before the trigger. It's just constantly capturing that piece of data or that portion of data. Now it's waiting to capture the remainder of the data for a trigger condition. So I'll just send the character lowercase a. So send that through, give the ILA, the hardware manager, just a moment to pull that data from the ILA. And we see that we've gone ahead, we've sent, the FPGA has received hex 61 when it says the data is ready. So if we take a look at our ASCII table here, we'll see that hex 61 is in fact a lowercase a. That's great. We can repeat that for other values. So if, for example, send a B. So just went ahead and rearmed the trigger and then sent a B, and look, we get 62 as we expected. So this is a nice and convenient way, like I was mentioning, just to make sure that your design is operating as you would expect. Of course, this is a relatively simple case, but currently working on a project, and I've worked on others in the past where you have more complex interactions occurring, and actually even a better example is you want to capture some data to provide to your simulation, right? So you have something occurring on an interface, that data, you can try to generate that data yourself using some logic or an external program to generate some sample data to provide your simulation. But what's better than the real world data, the actual thing that the FPGA is receiving, right? So use the ILA to capture that, save it to a CSV file, and then give it right to your simulation, make sure everything's working. I've used that plenty of times. It's honestly my preferred method for generating any kind of stimulus, or for providing any kind of stimulus. So with that, that concludes the demo for this workshop. And from there, we can go into taking a look at a couple of questions and answers.
So Eric, before we do questions, I did just want to pop on and let everybody know about some upcoming events and some upcoming training. So if you're interested in our paid training, we have our FPGA, Designing with FPGAs for Vivado series starting in March. So that's next week. There's 4 classes and they run every couple of weeks. So if you were interested in taking the entire series, the first one starts on March 5th. And I will drop that link into the chat panel for you. I'll also put the course calendar in there if you're interested in other training from us. As far as our webinars, and we also have workshops, we do one webinar, which is about an hour long per month, and we do one workshop, which is about 4 hours long per month. So for March, we have our workshop is Mastering Vivado Timing Constraints. And then our webinar is Demystifying Clock Domain Crossing. So I'll put those links into the chat panel for you. And not to overload you, but if debugging is something that you're really interested in, I do have additional events coming up on that topic. So we have our advanced debugging workshop. Again, that's 4 hours. It's in August, so I know it's a little while, but I'll put that link in for you. And then we also have Maximizing Your Debug with System ILAs coming up. I believe that's in June. So I'll put all of those links into the chat panel for you. I know it's a lot. When I send out the recording, I'll include all of that as well. So you'll be able to access it if you're interested. So I'm going to now turn it over to Eric to start answering some questions. And Eric, back over to you.
Yeah, thanks. Okay. So start with a couple questions. Seems like we got a decent amount here, so I'll try to get through the ones I can. So let's see. Starting off here. So what is the name for the 2 ways you showed to add debugged cores to the project? I'd like to look up some more information on how they work. So yeah, so we have 2 different ways, 2, I guess, higher level ways that you can add debug cores within Vivado. First way is your netlist insertion flow, and the second way is your HDL instantiation flow. So the HDL instantiation flow is where you directly add the debug core to your project and instantiate it like you would pretty much any other IP, right? You customize the IP, you give it a name, you put it in your project like you would any other entity. Now, if you're using HDL, of course, you instantiate it, put the component in there and hook it all up. If you're in Vivado Block Designer, just drag and drop the IP into the design like you would any other IP there. So those are the 2 different flows. We go into that more in depth within designing FPGAs using Vivado Design Suite number 3, if you're interested. Okay, there's another question here. Are you keeping ILA instances in production-ready designs? Personally, for our projects that we use here, we do not keep them in the production-ready designs. We have a more sophisticated Tickle build flow that builds our projects, and we have various switches within that flow that just can add or remove different portions of the design. And a portion that we can add or remove is debug logic. So for our internal builds, while we're testing, we have that switch turned on to just add the ILAs and various other debug cores that we want available to us. But then when we go to production, we go and we turn those off. Let's see. Let's see, is there also a way to add debug from the side panel, right click, etc.? Didn't mention it for any special reason. Let's see if I can try to show that there. Let's open that project back up. So I might be missing something here, but let's see. Once this opens. So I believe the question is asking, is there a way to add debug cores from the side panel? Like, I suppose there's a way you can add IP by going through the IP catalog directly. So you can do that. Like if you add, say we want to add another ILA, you double click on it, Vivado will ask you, do you want to create a new IP for the project just to be instantiated in like an HDL file, or do you want to add it to the current block design? You can decide which one you want from there. So that's a way you can do it from the side panel as well. Let's see, another question here. Are different techniques necessary for designs that involve the PS? No, all of these techniques, both the netless insertion or the HDL instantiation flow, you can use either of those um, with designs that have a PS, right? As remember, when we're here in Vivado, we're designing the programmable logic or the PL portion, the FPGA portion, if you will, of the MP-SOC. So we have access to the same things that we would on typical FPGAs. So you can go through the same flows that we showed here today, adding those debug cores to your block designs, building that block design, and then debugging with it. Let's see, any other things here? Let's see, can Block Designer automatically add debug cores to your block designs? So it depends, I guess, what you mean by automatically. So yes and no to that one. There is a way, if you saw when I was adding the ILA to the project, there is a mechanism within Vivado where it can automatically connect things for you, which is really nice. So for example, let's see if I can find, let's just get rid of this ILA, right? Say I wanted to put a system ILA on here. This is actually really helpful with larger designs. When I have like a number of different, I have an interface that I want to debug and a different control signals, I'll just go through, and if you control and click, you can select multiple things at a time. So say I want to select input interfaces or ILAs on these interfaces. I can right click and mark them as debug, right? And then you'll see this run connection automation pop up. And from here, you can go through and decide how do you want the debug core to be added to this. Now, specifically, this is working with the system ILA. So you can say, okay, well, I want the system ILA to probe these signals. And specifically, I'm working on the RX data. Specify what clock is relevant to this data. And then say that we want a system ILA. And then the same thing for that other pin that we added there. So we say we're using that same clock. And if I hit OK, it'll go ahead and it'll create a system ILA for us, connect up the probes, connect up the clock, and all that for us. Now, what's really nice is here, if you have a design with a number of different ILAs in them, it'd be kind of hard to keep track of which ones on which clock domains. So a thing that's really nice, and reason I like to use this flow is if you go and select another pin or another net that is debug and you run connection automation, if you specify that same clock that already has an ILA running, we'll see, it'll go ahead and just reconfigure the ILA that already has that clock on it and add just another probe for you, which is really nice. So you don't have a bunch of different ILAs all on the same clock domain and trying to sift through them in Hardware Manager. Can be a lot. This flow, uh, running the connection automation can really help with that as well. Let's see. Other questions here. So question, so the AXI option in the non-system ILA also decodes and marks AXI transactions. So what's the difference between the system ILA and the regular, just standard ILA? So the system ILA is I guess the primary difference in that regard really is that it allows you to select multiple different interfaces, right? So the different types of interfaces. The standard ILA can only accept a single AXI interface up to, right? Whereas the system ILA can accept multiple AXI interfaces, right? And all in the same ILA. Can also accept different kinds of interfaces as well. So that's really the main advantage to that there. let's see, there's clarification on the question. So there was a question earlier asking if you can add debug from the side panel. The clarification there is similar can be done from the side panel by going through open synthesized design and set up debug. Yes, so you can do that as well. If you're going through the netlist insertion flow, if you've marked nets as debug, you would go through those steps. So you open up your synthesized design, set up debug, and that would allow you to then say, hey, I marked these nets as debug, and I want you to actually put a core on that net. I want you to put an ILA on that net for me, so I have it available once I go through the remainder of the stages there. That is, of course, a different topic in itself. Which we cover more in designing FPGAs using Vivado Design Suite number 3. Let's see, another question here. Will having an ILA in the design affect the timing path? So the ILAs themselves, unless you have a design that has a lot of congestion, the ILAs themselves are completely synchronous devices. They have their own internal flip-flops and so on. So unless your design has other problems that are lending towards not meeting timing, then the ILAs themselves won't make it worse than it already is. Now, of course, these ILAs, they are consuming FPGA resources. They are created using your CLBs, your actual FPGA resources. So if you have a design that is fairly congested already, and you try to add a system ILA or a different ILA in there, it's possible that could be the tipping point where, okay, now there's just too much congestion and you're just running into timing problems. It does bring up a good point that the system ILA and the ILA, the debug cores in general, are synchronous devices. They should operate using synchronous data inputs. So like I mentioned earlier, finding the different probes and attaching them to an ILA with the appropriate clock. You want to, of course, make sure that you're only probing signals that are in that same clock domain that the ILA is running, right? Same is true for the other debug cores. Let's see, another question. Can you discuss ways to get sample data from the FPGA to the host? Is JTAG still the only way? If I'm building new hardware, what interface do I want to be sure to provide to enable this debugging? So you'd want to be using the JTAG there. That is going to, so there's another debug core, which isn't a core that you manually instantiate. It's one that's instantiated by Vivado when you go through the build process. It detects if you have debug cores within your project, and it'll create something what's called a debug hub. And that debug hub is what does the translation from the bscan interface, or JTAG in this case, JTAG here, over to the actual interfaces that the various debug cores are using. So you're going to want to make sure that interface is in the design. And on top of that, you're going to want to make sure that debug hub can run on a clock that is free running, right? So you want that clock to be always running no matter what. That way it can communicate with the hardware manager as necessary, and it doesn't have odd blips where it's not communicating and does some odd things, right? So there's a question here. Can you show an example of debugging over a remote connection through like SSH or remote debugging like Azure, AWS FPGAs? If not today, may you consider this for the next training? So yeah, that is a very that is an in-depth topic, something that we won't be able to get into today. I will just mention that we cover that within our designing FPGAs using Vivado Design Suite. I believe that's either the third or the fourth class. I'll have to take a look at the calendar or at the content of those courses. We recently, if you've taken courses with PLT before, you know we had our bootcamp series. The designing FPGAs using the Vivado Design Suite series is replacing that. So still getting used to exactly what content is in which of the courses. So question here, good question following up on the debug hub conversation. So is the debug hub always needed? How do we select the free running clock for it? So the debug hub, apologies, is needed if you have debug cores in your design. And that's the only case it's needed. Now, again, it's something that Vivado will add automatically to your project. Once you go through the synthesis step, it'll go ahead and create that for you and connect it up. Now, how do you tell it to always select a free running clock? Well, generally speaking, the tool will analyze the design, failure constraints, your pins, those kinds of things, and try to select the best clock that it thinks, or the best clock it finds to provide to your debug hub. However, if you have a design that's a bit more tricky and you want the debug hub to operate on a different clock, you can go through and manually say, hey, I want you, when you go through the synthesis stage, you can go through and say, hey, I don't want you to use that clock, I want you to use this clock instead. 9 times out of 10, like every time, I don't think I've ever had to go through and tell it not to, or tell it to use a different clock than the one it's selected. It's generally pretty good about finding the right clock. Let's see. Another question, do you have to rebuild, or would you have to rebuild, I guess, the whole project if you wanted to modify an ILA probe? So that is another one of those more advanced topics, one that we cover in designing FPGAs using Vivado Design Suite number 4. But just as a high level summary, there are a couple of different features that Vivado has built in that can help you out with this. First feature is the incremental compile flow, which allows you to reuse, or allows the tool rather to reuse previous build results to build new versions of the project. So for example, if you were simply to have the same project, right, you built it, right, then you want to go back and just change a probe. So what the incremental compile would do is would see, oh, okay, well, the only thing that changed is that probe. So as such, I only need to rebuild that portion of the design. I could just reuse the build results from the other portions. And then that speeds up the process pretty quickly. Another more advanced flow is the ECO flow. That's the engineering change order flow. That's where you're going and you're directly modifying the implementation net list. You're saying, hey, I literally want this net not to connect here. I want it to connect there. And then generate bitstream. It's a very, very fast process. We have labs for both of these things within the designing FPGAs using Vivado Design Suite number 4 course that goes through and shows you how to implement the ECO flow as well. All right, let's see, anything else? So looking pretty good on time. Got another 5 minutes here. So, okay. So yeah, so primarily work on the HDL portion of projects. And you want to get more information on the Vivado Block Designer. Do you guys have any references or maybe a course that takes a look at those? So yeah, the course I've been mentioning, a couple, or the series of courses rather, I've been mentioning the designing FPGAs using the Vivado Design Suite 2. Specifically, it does go into detail over how to use the various features of Vivado's IP Integrator, or otherwise known as the block design creation. Let's see, any other questions? I might have missed some, so there are quite a few here, but I do believe I've gotten every one so far. I believe that's all the questions. Apologies if I missed yours. Again, there's quite a few.
If
Through
we've missed
here.
your questions, go ahead and please redrop that into the chat panel for us. Or if you have any other questions, go ahead and put that in the chat panel now, and we'll get to it. Otherwise, I've been trying to keep up with Eric mentioning all of our FPGA courses. So I've dropped all of those links into the chat panel for you, as well as all of the ones for the workshops and webinars. So unless there's any additional questions, we really appreciate everyone for joining us today. Eric, thank you so much for sharing all of your expertise. So unless there's other questions, I think we'll go ahead. Oh, Eric, you got one more, so I'll go ahead and pass it back over to you.
Okay, great. Yeah, so we'll end on this one here then. So is there an easy way to save Tickle scripts used to insert the ILAs? So there isn't. Okay, there's a couple of different paths you could take with this. So the first path is if you have a block design here, you can ask Vivado to create a tickle script that will regenerate that block design, right? So you can do, I believe it's write bd tickle, if I'm remembering correctly. Yeah, so if you execute this tickle command, you can specify a name of the script. So bd.tickle, that's not bd, it's just a random name, I'll call it. And from there, it'll go ahead and create a block design or create a tickle script rather that will recreate the block design as it is. So now if you want to create a script that can, do something like I was mentioning earlier that can optionally add ILAs, optionally connect ILAs, you can of course create your own custom tickle scripts. And the easiest way to find the commands that you should add that add the ILAs and configure them is simply just to look at the tickle console here. So the way I usually do it is if I want to add a new IP, so if I'm adding another, let's add a VIO. So if I'm adding a VIO to design, I'll just do it in the block designer. And then right here, bam, there's my command to go ahead and create that cell, to create this cell. Then from here, if I want to go ahead and modify it, say 4 or 3, 6, why not, right? Then it'll spit out the commands to perform those modifications or those customizations of the IP that I've just done. So I'll just go ahead and I'll copy this, put it in my own custom tickle script, and then there we go. Now we have it actually creating the VIO. From there, of course, you then have to connect the VIO to things. For example, if I were to go ahead and make that external, way you can do that is by simply clicking on a pin and hit Control T, and that'll just make the whatever pin you've selected as an external port on the block design. Then copy that command, right? And then if you have different commands to connect this up to something, I have nothing to connect it to because everything's connected in this design. But if you were to connect it to any of these signals, you just copy the associated tickle commands right there and put it into your custom script. So I hope everyone has enjoyed the webinar here today. I appreciate all the questions and hope to see you guys soon in a upcoming training.
All right, we appreciate everyone for joining us. And Eric, thanks so much for sharing your expertise.
Absolutely. Take care, everyone.